All right, guys, so today what we're going to do is we're going to be talking about rational functions. And so basically everything we've done in the polynomial unit so far is leading up to this topic of rational functions. So we're going to start looking at functions that take two polynomials and divide them by each other. So the top and bottom are both going to be polynomials. And again, the goal of this is going to be able to graph them accurately. Okay, so we're going to think about what these graphs will look like in the end when we divide them. All right, so let's see some of our rules. Okay, so here are some examples. 1 over x, okay, both of them are polynomials, so it's a rational function as well as all of these. Okay, so these are all rational functions, and they all behave like rational functions do. Now, here are some non-examples, okay? So if I have 2 over the square root of x, that is not a rational function, because if you remember, the square root of x is kind of like x to the 1/2. And remember that polynomials have to have positive integer powers. Okay, and clearly sine of x, not a polynomial. Absolute value of x, not a polynomial. So these won't work. All right, so the very first thing that we're going to talk about are the asymptotes of a rational function. So the asymptotes, both vertical and horizontal. Now, if you don't remember what an asymptote is, typically how you're taught in Algebra 2 is it's an imaginary line. So imagine that's a dotted line that our graph gets really, really close to, but never touches. Now, that's not the exact correct definition. If you want the exact definition, just call me over and I can explain it to you. But for our purposes, that definition will work. Okay, so the very first thing, we have vertical asymptotes at the zeros of the denominator. So if you remember, bad things happen when our denominator is equal to 0, and those things are formed by asymptotes. So for example, if I know that if I sub in 3 and get a 0 in the denominator, I know that at 3, okay, I'm going to have this vertical asymptote that causes my graph to do weird things. Okay, and so all that time we've spent finding zeros of polynomials have led up to rational functions and being able to find zeros still. All right, the other type of asymptotes are horizontal asymptotes. Okay, so obviously these ones go vertically. Horizontal ones are going to go this way. Okay, so for example, I'm going to have something that goes like that and something that goes like that. Okay, so we have 3 rules that we have to think about. Now, what I'd rather you do is not memorize the rules, but think about what's happening in each of these situations. Okay, so first rule, if the degree of the numerator is greater than the degree of the denominator. So let's do an example. Let's say that we have x squared over x. Okay, so clearly the top has a degree of 2 and the bottom has a degree of 1. If you imagine as this thing approaches infinity to the right, and I sub in positive infinity and positive infinity, which one is going to be bigger? Okay, so is infinity squared bigger or is infinity to the first power bigger? Now, hopefully you said that infinity squared is bigger because that's infinity times infinity. Okay, it's infinitely greater than the denominator. So if you imagine that is going to cause the end of my graph to increase constantly. So it's going to continue going up because the top is just so much bigger than the bottom. Okay, so when the top is bigger than the bottom, there are no horizontal asymptotes. So there's nothing bringing us back down. All right, in the second case, if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at 0. So let's flip this and say What if we had x over x squared? Okay, well now the bottom is really, really big. And if you imagine when you divide by really, really big numbers, okay, then our numbers are going to start going towards 0. Okay, so if you imagine, just think about the chain of numbers like 1/2, and then 1/3, and then 1/4. That's a 3. 1/5, and so on. All of these numbers, as these approach 0, or as these approach infinity, my overall number approaches 0. All right, and lastly, okay, so we did a greater than and a less than, and finally, if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote occurs at the ratio of the leading coefficients. So let's look at that. So if I say f of x equals 3x squared minus x over 2x squared plus 1. Okay, so if you notice, the degree is 2 on both polynomials. So if, again, we think about this idea of subbing in infinity, okay, so infinity is going in for x. Well, these really aren't going to affect our equation that much because here we have infinity squared and infinity squared. So anything added or subtracted to that doesn't affect my number very much. And so imagine this, we have something sort of like 3 times infinity squared over 2 times infinity squared. And if you think, now, these don't exactly cancel out, but you can kind of picture it that way, that these two things kind of cancel out, and what I'm left with is the ratio of the leading coefficients, 3 over 2. So that is where my horizontal asymptote would be. All right, so let's practice finding our asymptotes real quick. All right, so I'm going to do this first one over here. And I'm going to look for vertical asymptotes. So remember that vertical asymptotes occur when the denominator has zeros. So if you think about this, one thing that'll help me is if I factor. So this is a difference of perfect squares. So I get x plus 1, x minus 1. So my two zeros are x equals -1 and x equals +1. So I'm going to say that I have vertical asymptotes at x equals -1 and x equals +1. Okay, and that's all I have to do. The horizontal asymptotes, remember that I need to look at the degree of the numerator versus the degree of the denominator, and you'll notice that they are equal. And if you think back to our last part, if the degrees are equal, then the horizontal asymptote is at the ratio of my leading coefficients, which is 2 over 1, which is 2. So if you can imagine, if I were to draw my asymptotes real quick, I'd have a vertical one at -1, a vertical one at -2, and a horizontal one at +2. Okay, and that would affect my graph in a way that we'll look at in a little bit. All right, so let's do another one. Let me get rid of this real quick. Okay, so let's look at this second one. I'm going to do it in blue, okay, this one. And again, I'm going to factor both the top and the bottom. So if you look, this is going to be x, let's see, plus 2, x minus 1, all over, let's see, x minus 3, and x plus 2. All right, so you'll notice something interesting in this one, that x plus 2 is actually going to cancel with x plus 2 right there. And so I'm only left with x minus 1 over x minus 3. All right, so if I think about my vertical asymptotes and my horizontal asymptotes again, my vertical ones happen at the zeros of my denominator, and in this case, that's only at x equals +3. Okay, it's whatever makes that 0. And then my horizontal one remember again that I'm looking at the degree of the top versus the degree of the bottom, and they are equal in this case. So the ratio of the leading coefficients is just 1 over 1, which is 1. So that would be at y equals 1. Okay, so those would be my two asymptotes in that case. All right, and we'll do this last one. Okay, and I have 1 over x plus 2. So vertical asymptote, horizontal asymptote. All right, so this one's pretty easy. It's already factored out for me as far as it can go. And so the only thing that makes the denominator equal to 0 is x equals negative 2. And for the horizontal asymptote, notice that on top I have no x's, and on bottom I have an x to the first power. So the bottom is bigger in degree. Okay, so when the bottom is bigger in degree, then I have y equals 0 as a horizontal asymptote. All right, as always, if finding asymptotes doesn't make sense, make sure that you call me over so that I can help you out. All right, just like we were doing with graphing polynomials, we want to set a standard for what we expect to see when we're graphing rational functions. So I've made a list of things that you need to be thinking about when you're accurately graphing these rational functions. So the very first thing that you do is you have to simplify f of x. Okay, if anything can cancel out, you need to make sure that you cancel those things out. Okay, find and plot the y-intercept. So just sub in 0 for all your x's and plot whatever your y-intercept would be. Thirdly, you're going to find the zeros of the numerator. These are going to be the zeros or the x-intercepts of your graph. Okay, so those are your x-intercepts. The zeros of the denominator are going to be your vertical asymptotes. Okay, and then you're going to finally use the rules we talked about to determine horizontal asymptotes. And then you're just going to pick a few test points, okay, to kind of figure out where your graph is going to be, and then you're just going to complete it using smooth curves. All right, so the next few examples, I'm going to take you through this process and kind of see what this all means. Okay, so let's start with an easy one. I'm going to start with this one right here. Clearly has a vertical asymptote at x equals 2, okay, because 2 makes the denominator equal to 0. A horizontal asymptote at y equals 0, because the power of the numerator is smaller than the power of the denominator. It has no x-intercepts because there's no zeros in the top. Notice that the top is just 3, so it never hits the x-axis at all, which makes sense because I have a horizontal asymptote there. And the y-intercept, if I sub in 0, okay, if I sub in 0 right there, I get 3 divided by 0 minus 2, which is negative 3 halves. Okay, so let's plot what I know. I'm going to do my, okay, so we'll say that's 1, that's 2. So I'm going to put my vertical asymptote here at 2. Okay, I'm going to do a horizontal asymptote right at 0, so that's right on the x-axis here. Okay. Let's see, we have no x-intercepts. We have a y-intercept at negative 3 halves. So that's, if I go 1, 2, it's like right there. Okay, now, you can kind of see, based off, if this right here, let me get my laser pointer. If this right here is a point on the graph, it's enclosed by these asymptotes right here. So what that tells me is, as I draw this, I know that my graph has to go through here. And if it does that, it's going to approach that asymptote and flatten out going down to negative infinity. Likewise, through this point, it's going to flatten out and go to negative infinity in that direction. Okay, so what I need to do is I need to test some point out here to see if I need to graph it above the x-axis or below the x-axis. So really all I care about is whether it's positive or negative. So what I'm going to do is I'm going to look at 3 here, and I'm going to sub it into my equation. So if I think about 3 over 3 minus 2, is that positive or negative? Okay, so you're going to go 3 over 1. Okay, that's positive 3. So 2, 3. So that means that point is right about there. So if you sketch your graph, this thing is going to go up this way and then down through this point and flatten out as it approaches the horizontal asymptote. Okay, and so that's just a rough sketch of how we want to graph these rational functions. Okay, as always, again, if this didn't make sense, make sure that you call me over. We'll do another one here at the end of this video that will also be pretty comprehensive. Okay, so the last thing we need to add to our graph are the holes. And you may think, what are holes? Obviously, we haven't covered that before in any class prior. Okay, so sometimes a factor will appear in the numerator and the denominator. If there is an equal amount of that factor in both the numerator and denominator, meaning like if I had x minus 1 squared on top, I'd need an x minus 1 squared on bottom. I'd need 2 to cancel out 2. There's going to be a hole in your graph at that x value. So for us, that would have been at x equals 1. Okay. If there are more factors in the top than the bottom, okay, the resulting zeros are x-intercepts. Okay, so for example, let me write the second example. If I had x minus 1 squared over just 1 x minus 1, this would cancel with one of those. So I'd still have a 0 or an x-intercept at x equals 1. Okay, so it's got to be the same number. Okay, if there are more factors in the bottom, okay, that results in vertical asymptotes. So again, using this example, okay, the top cancels with one of the bottom ones, and I end up with a vertical asymptote at x equals -1. Okay, so that is how we get holes, is when something perfectly cancels with the top and the bottom. All right, so let's see how this is all put together. This example, whoops. All right, so I have this equation. The very first thing I do is simplify. So I'm going to simplify this to x minus 3, x plus 3, all over x minus 3, x plus 1. All right, so clearly x minus 3 cancels with x minus 3. And so what we just talked about, we know that we're going to have a hole at x equals 3, okay, because I have an equal amount canceling out. So overall, I'm left with x plus 3 over x plus 1. All right, so let's figure out all of our asymptotes and our x-intercepts and y-intercepts. Okay, so vertical asymptotes. What makes the bottom 0? That would be x equals -1. Okay, horizontal asymptotes, remember that we look at the degree of the top versus the degree of the bottom. Okay, it's equal, so that's a ratio of the leading coefficients, so 1 and 1. So at y equals 1 over 1, which is 1, I have a horizontal asymptote. Now, the x-intercepts are the zeros of the numerator, which in this case are x equals -3. Okay, and then the y-intercepts, okay, this is where you're going to sub in 0. Okay, so if you imagine sub in 0 there, sub in 0 there, sub in 0 there, everything goes to 0 except for -9 over -3, which is +3. All right, so let's look at a graph. Okay, so the very first thing I'm going to do is make my marks like that. And sort of like that. Okay, so let's do our vertical asymptotes first. So at -1, I have a vertical asymptote. At +1 on the y, I have a horizontal asymptote. I have an x-intercept at -3. That's right there. and I have a y-intercept at positive 3. 1, 2, 3. Okay, and already you can kind of see what this is going to look like. Okay, with this down here, okay, that tells me that that's kind of barricaded in there, so it's going to kind of look like that, okay? And then for ours up here, it's kind of barricaded in by that one and by that one. Now, the only thing I have to keep in mind is my holes. Okay, so I have a hole at x equals 3. That's way out here. And I haven't graphed that far, so I need to make sure that I do that. Okay, so when I graph this, I need to put just an open circle at 3 so that when my line goes through it, it hits and jumps over that point. Okay, and that's all you got to do. Okay, so that would be as accurate of a graph as I would expect all of you to be able to make on all of your practice problems moving forward. So again, the goal of this is to be able to graph rational functions. That's what your practice is on. It'll be on the unit test next week. So again, if you need any help, just let me know. Thanks for watching.